Hello dear viewers, my name is Hopane. Today I will show you a very important video lesson on geochemical studies of oil, part 2, practical interpretation of the results of oil biomarker analysis carried out in SIM, MRM and full scan modes. For me, this topic is very interesting and important as it is completely related to the topic of my master's thesis at Newcastle University in England. If you want to interpret the results of biomarker analysis yourself, I recommend watching this video lesson till the end. This slide provides a brief information about myself. I have 13 years of experience in interpreting geochemical data in practice. I am the founder and still the head of the Geochemistry Lab of Chemistry Engineering. Over the last 9 years, we have conducted geochemical studies on about 7,000 oil samples derived from 160 oil and gas fields in Kazakhstan and Russia within the framework of about 100 projects. I am also an expert in the field of geochemical studies of oil, gas, core and formation water. In the first part of the seminar, I showed you the interpretation of the results of gas chromatography analysis of oil and the visual application to substantiate the physical and the chemical purposes of oil. In this lesson, I will show you the practical interpretation of the results of oil biomarker analysis in detail. This topic is very extensive and my training on this topic usually takes up to 5 days, but here I reduce the material as much as possible to fit into 30 minutes. First, let me explain you what biomarkers are. In medicine, biomarkers are used as well, but biomarkers in medicine are tests that can be used to monitor body activities and the development of disease in humans and animals. Biomarkers in medicine should not be confused with biomarkers in oil and gas industry. Oil biomarkers are fossil biomolecules that are part of oil and can be used as remains of organisms to interpret the age, type of organic matter and environmental condition of the source rock. So biomarkers are substances formed in oil when it was formed in the Earth's crust. That's why the relative concentrations as ratios are directly related to the conditions of oil formation. Hydrocarbons from C5 to C40 are usually found in oil. Biomarkers in oil are found in the number of hydrocarbons from C19 to C35. I often hear a question like, "A biomarker is found in petroleum products or not?" Well, gasoline range contains hydrocarbons from C5 to C10, which means there are no biomarkers. In kerosene, the hydrocarbon range is from C8 to C15, so there are no biomarkers as well. The hydrocarbon range of diesel is up to C23, so only C20 up to 23 biomarkers can be identified there. Biomarkers are found in saturated and aromatic fractions of oil. Before conducting biomarker analysis, we separate the oil sample into saturated and aromatic fractions. The main 4 types of biomarkers in the saturated fraction are steranes, isosteranes, terpenes, and diesteranes, while the main 5 biomarkers in the aromatic fraction of oil are mono and triaromatic steroids, dibenzosphins, phenanthrene, and methylphenanthrene. Ions by which we can determine the biomarkers are presented in brackets. There are 3 modes for identifying biomarkers in oil using GC-MS. The first and the most common method is SIM, that is single or selective ionization method. Its advantage over full scan mode is that SIM focuses only on the specified ions and therefore the sensitivity and the signal to noise ratio are high. But the disadvantage of SIM compared to full scan is that the operator who creates the method and conducts the biomarker analysis must know the ions he needs in advance. For instance, 217th ion for styrene, 191st ion for terpene, and so on. In the last slide, I already showed you 9 necessary ions for biomarker analysis. But in full scan mode, the operator doesn't need to select the desired ions when creating the method, because in this mode, up to 600 ions are simultaneously captured, and the operator can select the ions later. But it should be noted that such simultaneous fixation of ions worsens the sensitivity and the signal-to-noise ratio. The second advantage of full scan mode is that identification of unknown components in oil by comparing the mass spectrum with the mass spectra in the library. MRM, multiple reaction monitoring, is the most in-depth study of oil biomarkers. Metastable reaction monitoring mode has advantages of SIM. It monitors the desired parent and the daughter ions during a metastable transition using a dual focus magnet. In our geochemistry laboratory, we conduct biomarker analysis using two instruments. The first instrument is a gas chromatograph with mass spectrometer. So here you can carry out analysis in SIM and full scan modes. The second instrument is a gas chromatogram equipped with a triple quadruple mass selective detector, which consists of two analyzers. The first analyzer gives the parent ion, the second analyzer captures the daughter ions. Therefore, here it is possible to additionally conduct biomarker analysis in MRM mode. I will not explain in depth the operating principle of these equipments. This is presented in my another work. Let's start identifying biomarkers in oil in SIM mode. We have already said that biomarkers in oil are found in a number of hydrocarbons from C19 to C35, and you need to know three ions. There are 191 for terpenes, 217 for steranes, and 218 for isosterenes. Just using ion 191, all terpenes from C19 to C35 can be identified. First, tricyclic terpenes come out, which are shown here as TT, then Hopanes, C29, C30, and at the end, homohopanes come out. On the mass chromatogram, steranes come out, first C27 disterenes and steranes, then C28, and then 29 disterenes and steranes. If it is difficult to learn, to understand, for beginners, there are two ways to identify steranes in SIM mode. The first one, if you compare mass chromatograms of steranes at the ion 217 and 218 together, then the peaks T27, 28, 29, alpha, beta, beta elute at the same time. If we compare mass chromatograms of steranes at the ions 217, 372, 386, 400 together, then the peaks of steranes elute at the same time depending on the molecular weight. The same principle is true for terpenes. There are two ways to identify terpenes in SIM mode. The first one is to memorize the complete list of components. The second one is if we compare the mass chromatograms of terpenes by combining ions together, then the peaks of terpenes appear on two mass chromatograms at the same time depending on the molecular weight. For instance, C27 terpenes come out simultaneously at 191 and 370, C28 terpenes at 191 and 384, and so on. Identification of oil biomarkers in full scan mode. If the oil is highly biodegraded, some steranes and terpenes get lost there, which makes the integration difficult in SIM mode. then it is better to conduct biomarker analysis in full scan mode so that the library itself could recognize unknown peaks by comparing the mass spectra. If you do not have a library, then we can also recognize peaks ourselves just by reading mass spectrum and integrate the peaks. Let's say we did biomarker analysis in full scan mode, and we got the following distribution of styrene on the mass chromatograph ion, where we need to identify the unknown component A. If we click on this peak, the mass spectrum of this peak A will immediately be opened below. The scan time is indicated in brackets. It corresponds to the time when the peak eludes. To read mass spectrum of styrenes, I need two tables. In the first table, M plus is the molecular weight of styrenes. For example, the molecular weight of C27 is 372, and the M minus 15 is the molecular weight of a free radical or methyl group, that is CH3 15. The second table presents the criteria for determining styrene isomers. If ion 149 is higher than ion 151, then alpha. If they are similar, then beta. If ion 217 is higher than ion 218, then alpha. If the opposite, then beta. To determine the number of carbons in the mass spectrum, you need to look at the last two dominant peaks. Here they are 372 and 357, marked with rectangular. This means, according to the data in the first table, this peak is C27 styrene. To determine carbon isomers in the mass spectrum, it is necessary to compare ions 149 and 151, also 217 and 218. According to the second table, 149 is greater than 151 ion, which means alpha. The second one is 217 ion is greater than 218 ion, which means also alpha. If two are alpha, or second is also alpha, then the third will automatically be alpha. So we were able to determine the unknown peak from the mass spectrum, and that is C27 alpha 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 styrene. But the disadvantage of this method is that it is impossible to determine S and R configurations. Here is another example. The same mass chromatograph at ion 217, where it is necessary to identify the unknown component B from the mass spectrum. Click on this peak, and the mass spectrum of this peak will immediately appear below. Here you can look at the last dominant two peaks. They are 400 and 385, which corresponds to the molecular weight of C29 styrene and minus the methyl group. That is our unknown peak. B is C29 styrene. To identify carbon isomers in the mass spectrum, a comparison was made between the two peaks. 149 is lower than the ion 151, which means beta, which means it is also alpha. The second is also alpha, then the third will be alpha as well. So here we could determine the unknown peak B from the mass spectrum, and that is C29 beta alpha alpha styrene. When identifying terpenes, a similar approach can be applied. For example, we need to identify unknown peaks A, B, C from the mass spectra. To read the mass spectra of terpenes, we need to understand this reference book. On the mass spectra, there are two predominant peaks, 355 and 370. They are, according to the table, C27 terpene. Regarding the isomerization of terpenes in two mass spectra, A and B, 191 ions are higher than 149 ion, which means alpha beta. In the third mass spectrum, C is opposite. So the opposite is true for C. So it is beta alpha. So as you can see here, therefore, we could identify unknown peaks from the mass spectra of terpenes as well. Identification of steranes and diesteranes of oil in MRM mode is presented here. On the mass chromatogram of MRM mode, biomarkers are represented by two ions. The first ion is the parent ion, which corresponds to the molecular weight of the biomarker being determined. The second ion is the daughter ion, which corresponds to the place where the biomarker fractionation occurs. Daughter ions are like in SIM mode. Therefore, to make it clear, let's use the term channel for the mass chromatogram of biomarkers in MRM modes. In MRM mode, each diesterane and styrene is separately shown on each channel depending on the molecular weight. For example, on channel 372217, there are 4 isomers of C27 diesterenes and styrenes, and on channel 386217, similar peaks of C28 appear, and so on. When identifying terpenes in MRM mode, a similar principle approach can be applied. So C27 terpenes elute on channel 370191 to identify further terpenes as C28 and C29 terpenes. We add another 14 ions, which is a molecular weight of /2, while daughter ions stay unchanged. So biomarker analysis is used to determine the characteristics of source rocks of the studied oil samples in terms of environmental condition, lithology of organic matter, thermal maturity, and the age of source rocks. We can also use these genetic parameters for genetic typing of oils and discerning genetic link between these different oils. Hydrocarbon source rocks can be deposited in different environmental conditions, marine, lacustrine, deltaic, in which certain microorganisms and biomasses exist. Oil biomarkers retain information about these parent organisms, and their analysis is used to predict environmental condition of the source rock. Steranes are abundant in oils derived from predominantly marine organic matter, and their low concentrations are typical of lacustrine and coastal marine organic matter. Based on this, the crossword pristine fighting against C29 styrene C30 Hopane ratio can be plotted after their integration in SIM mode. Pristine fighting values can be derived from GC as well. Here is an example for the oil fields of South Mankschlag Basin. If you are interested to read this paper, you can scan the QR. Similar graphs are plotted for other plant basins. For example, in eastern part of the Caspian Basin, oil from pre-salt and post-salt fields have different organic matter environments. Although all are located in the marine environment, oils derived from South Turkey and Shu Sarasur basins were generated from soft rocks deposited in lacustrine environments. The presence of styrene in oil indicates a marine organic matter, while a high concentration of tricyclic polypropylene or TPP suggests lacustrine organic matter. They are difficult to identify in SIM mode, but are easily determined in MRM mode by these ions. Therefore, biomarker analysis of some representative oils should be carried out in MRM mode to compare the conclusion with that in SIM mode. So here, the results are consistent. Lithology of soft rocks which generated standard oil samples can be visually predicted on this mass chromatogram of terpenes using these 4 criteria. Based on that, the first plot and the terpene ternary can be used. As an additional parameter, aromatic fraction can be used as well. If the concentration of sulfur-containing compounds such as dibenzothiazine is less than phenanthrene, then the oil was generated from shaly organic matter. If the opposite is true, then the oil is likely to be generated from carbonate source rock. Based on this, we created a geochemical atlas of oil based on lithology of the organic matter. We used 3 circles to classify them. If oil was generated from shale source rocks and the field is located in terrigenous sediments, then we marked it with a green circle. If oil was generated from carbonate source rocks and its field is located in terrigenous sediments, it was marked in yellow. And if its field is located in carbonate sediments, it was marked with a red circle. As shown in the map, yellow and red circles dominate in the southern part of the Caspian Basin, while red circles dominate in the northern and the eastern parts of the Caspian Basins. In other basins, green circles predominate. Okay, so here let's determine the lithology of the source rocks of oils using our biomarker parameters. You have 3 minutes. Okay, here are the results. Yes, the first 3 oils were generated from shale organic matter. The rest were generated from carbonate organic matter or source rocks. If we compare the results with the physicochemical properties, then on this slide you can see that oils from shale source rocks have a relatively low sulfur content compared to oils from carbonate origin. This observation can be seen in most of the fields of the Republic of Kazakhstan. The maturity of source rock is a function of temperature and time, how much heating has experienced. This is related to the extent of hydrocarbon generation and accurate and is thus a critical part of source rock evaluation. Many different maturity parameters are used in the assessment of thermomaturity of source rocks, mainly based on optical or pyrolysis. However, none of these can be used for oils. Instead, the molecular composition, as shown on the left side, is used to assess the thermomaturity of the source rock of an oil. As you can see on the right side of the slide, there are 3 stages of thermomaturity during hydrocarbon generation: early, peak, and late maturity. One of the important implications of thermomaturity for geology is that oils from early field reservoirs usually show the relatively lower thermomaturity than hydrocarbons that fill the reservoir later. So relatively higher mature oils are usually found near the source rock of filling in the reservoir or kitchen. There are many parameters used to determine thermomaturity of oil. as you can see on the left side of the slide. Among them, the most popular are styrene, terpenes, and so on. With increasing thermal maturity of phosphor, the chemical molecule of styrene converts into isomers firstly under thermal stress. The chiral center at C20, initially exclusive biological derived 20R isomer, is converted to a near equal mixture of 20R and the geologically stable 20S epimass. Secondly, at the same time, with maturity increase, isomerization at the C14 and the C17 chiral centers converts biological derived alpha 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 into more geologically stable alpha beta beta isomers, but of C27, 28, 29 styrene isomers, only C29 styrene is used to determine the thermal maturity in cyan mode, because C27 and 28 styrenes and distyrenes co-elude together in the mass chromatogram of 217, leading to incorrect peak integration. Now I'll explain how to visually determine maturity of oil on mass chromatogram. As maturity increases, the first peak, which is C29 alpha 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 S, increases due to a decrease in the fourth peak, which is C29 alpha alpha R. At the same time, there are two peaks between them, which are alpha beta beta, that increase with maturity. Therefore, the second sample is more mature than the sample number one. But the disadvantage of styrene isomers is that they are not reliable for highly mature samples, and it should be noticed that biodegradation affects these parameters as well. Therefore, terpenes such as Hopane and Hopane should be used to assess the thermal maturity of even relatively higher mature samples. With maturity, Tm in oil converts into Ts. Therefore, the first sample has higher thermal maturity than the sample number one. We usually use plots of isomerization of styrenes and terpenes together, because terpene maturity parameters usually exhibit low thermal maturity for oils derived from carbonate source rocks. For example, oils from pre-salt carbonate sediments show relatively low thermal maturity compared to oils of post-salt carbonate and shale deposits in the eastern part of the Caspian Basin. Application of aromatic hydrocarbons as indicators of the maturity of source rock is becoming increasingly popular. The most reliable are triaromatic steroids, methyl dibenzothiazine, and the methylphenanthroid indexes, as their values increase with increasing thermal maturity of the oil. For example, C20 and C21 triaromatic steroids increase due to a decrease in the concentration of C26, 27, 29 triaromatic steroids. Therefore, the second sample is more mature than the first one. As for the visual assessment of maturity by MDBT, increases, which is methyl dibenzothiazine index. The first peak for MDBT increases due to a decrease in the third peak, which is 1 MDBT. Therefore, the second sample is more mature. As for visual assessment of maturity by methylphenanthroid index, with maturity, the high blue peaks, which are 3 MP and 2 MP, increase, and the remaining peaks decrease. Let's say you are presented with results of geochemical analysis and PVT data of oil properties. Gas content, saturation pressure of two oils, G2 and G9. You are also given geochemical data, which are chromatograms, mass chromatograms of these oils. Based on this available data, you need to explain physicochemical properties and purity data of these oil samples. You have 2 minutes now. Well, here's the answers of this exercise. The high values of density, viscosity, and acid number of these oils are probably caused by high biodegradation, as indicated by the presence of UCM, unresolved complex mixture. The relatively high sulfur content is probably due to the fact that the oils are generated from carbonate source rocks, as evidenced by 4 parameters in the mass chromatogram of terpenes. The minus values of the per point in oils are explained by the fact that the studied oils are generated from marine organic matter as indicated by the distribution of N-alkanes on their chromatograms. The relatively low gas content and the saturation pressure in these oils are due to low thermal maturity. The source rock deposits in different geological times contains certain biomass which serve as source of organic matter. The found remains the relative concentration of these microorganisms in the composition of oil, enable to determine the age of the source rocks of the studied oils. C28-29 styrene ratio usually increases with geological times. The values for source rocks older than pre-Devonian age are low, less than 0.5, while those from Devonian to early Jurassic ages are 0.5 to 0.7, and for source rocks younger than Jurassic, their values are greater than 0.7. Let's do a practical task together. You are presented with a table which has a data, and for oils A and B in MRM mode, determine the potential oil age of the source rocks for oil A and B. Are they genetically related or not? If we sum up all 8 peaks of C28 styrene and divide them by 8 peaks of C29 styrene, then the obtained value for A is greater than 0.7, which means late Jurassic or younger. The same ratio value for B is less than 0.5, which means early Devonian or older age. Therefore, they are genetically different. If your results are obtained in SIAM mode, you can use 4 peaks of C28 and 4 peaks of C29 styrene to calculate this parameter. Also, expanded tricyclic terpene ratios can be used to determine age, as can be seen on the right side of this slide. Dinostyranes. This parameter is very difficult to use to determine the age of source rock, as in the vast majority of world literature, the presence of dinostyrane in oil indicates Triassic or young age of the source rock, according to Peters, very famous geochemist. Dinostyrane may also be present in oils from Paleozoic source rocks. He also noticed that 4-methylstyrene occur in oils from Mesozoic source rocks, but are absent from Permian and most carbonate rocks, with some exceptions. In the Paleozoic oils of one field X in Caspian Basin, dinostyranes are identified, which are absent in oils of another field in the Pozachi Basin. No cholesterol and no dicholesterol ratios can be used to calculate the age of source rock. To make it clear to you, I use numbers here instead of the long names. You can determine the height of each peak visually for calculation. Formulas and plot are also presented here. As you can see, this plot is useful for Jurassic or younger ages. Using this data, you should determine the age of the source rock of oil XXX. This is the Russian field for which we did research here in Kazakhstan. So what did you get? Yes, This is roughly value. That's why, as you can see here, with this Jurassic age. Cluster analysis of PCA. Genetic typing of oil is based on the distribution of the most important biomarkers. Correlation oil means a comparison of geochemical composition of at least two samples to determine whether there is a genetic link between them or not. Statistical analysis can be carried out in MRM and PIGI software in order to identify the similarities and the differences of oil in terms of quantitative and qualitative biomarker composition. For genetic typing of oil using cluster analysis, it is recommended to use genetic age parameters, parameters of lithology and environmental condition of organic matter. For example, an oil spill occurred, let's say, on the surface of the Caspian Sea, through which only tankers A, B, C, D, E pass. Based on the results of PCA analysis, based on the biomarker composition of oil, determine which tanker could have spilled oil on the surface of the sea. How do you think? Yes, tanker A may be the source of this oil spillage. You are presented with geochemical data for 3 oils. Use these 6 symbols that we showed you in the seminar. If the oils are biodegraded, then mark them with triangles. If not, then with green rectangle. So you should characterize them. Okay, so did you get such a picture here? Now you can use them to substantiate the physical and chemical properties. As you can see here, oils of carbonate have higher